awake.
Well, as you guys have been noticing recently, I've been kind of sometimes having in class and sometimes not. And that's because it's exactly what Caleb said. He said, I can't believe I'm awake. Because, sometimes, because we have the flexibility this semester to like record classes and publish them, that means that, if you feel like your health is waning, if you feel like you're not doing so good and you need some extra rest, then yeah, you can do things virtually. Other times when you're doing okay, then you can switch to in-person. So the goal is to not, I didn't bring my chalk, so I have some chalk here. The goal is to not, the goal is to never have to resort to that, but sometimes it just happens. Are you guys able to see the orange? I think I remember people saying that on the video, the orange isn't showable. I'm gonna have to go with the yellow now. There's a lot of writing though, so I'm gonna have to actually go get some of my chalk. That yellow will not last this time.
I had 15 hours of sleep. No.
Go
I mean, I don't know how I'm awake right now.
Yeah, a lot of stuff you would think.
Yeah. And also, I just don't like sleeping. Sleeping sucks sometimes.
There we go. You keep the chalk. All right. Mining 13.2. Let's talk about line integrals. Let's say we have some curve. All right. Well, we can partition this curve P1, P2, P3. This is some curve C, all the way to, let's say, some PI minus 1 to some PI star, where, you bring this down here, you bring that down there. This is at some XI star, YI star, okay? All the way here to some PN. We partition the curve C that is on the XY plane, and here's the catch. The X and Y coordinates are parametrized utilizing an independent parameter T, meaning this curve has some TI such that f of some TI minus 1, such that some f of TI minus 1 goes here, and some TI star such that f of TI star goes over here. And we can also call this PI, or some TI goes here. Well, I mean, does this seem like a crazy situation? Not really. We've actually done parametric equations, set x equal to a function of t, set y equal to a function of t. And let t range from like A to B. That's the parametric version of things that we've been doing all semester long. Here's the vector version. And as you know, this is the same thing as x of t I hat plus y of t j hat. Okay. Assuming C is smooth and R prime is continuous and R prime of t does not equal 0, we can divide this interval A to B. There's B, there's A. We can divide that interval up into n subunits, okay? And those subunits map to these subarcs. These are the subarcs that the subunits would map to. So this subunit would map to this subarc. Okay, so assuming that your function f of xy has a domain that includes the curve. Here's the domain D of f of xy. Assuming that your function has a domain that includes this curve in it, then here's what we can say. That what would this be? Notice that this is just a difference in width. Notice that this is just a difference in height. Height times width.
Area.
Yes.
Is that a delta S?
Delta SI, yeah. Like a small piece of arc. Like this orange here. And actually, your delta SI can be thought of as B minus A divided by N. Because we're breaking up A to B into N chunks, N equally spaced out chunks. So we notice that this would approximate the this would approximate the area under the curve C. So what are we doing here that's different than before? Well, before we had a function. In single variable integration, we had a function and we integrated the function, and that told us the area underneath the curve. But now we have something that is much more robust in nature. Yeah, it has a lot more, it is way more dynamic because it is a parametric curve. You know how functions have to obey the vertical line test, this and that. Parametric curves don't have to do that. Parametric curves are what allow you to draw, heart-shaped symbols and crazy-looking graphs. And we can actually integrate things with these parametric curves versus just functions. So now we're learning how to integrate the area under a parametric curve. Okay, so if this approximates the area, then the limit as n approaches infinity will actually be equivalent to this integral right here, the line integral. This is called the line integral, where we're integrating, where we put that C because we're integrating with respect to that curve C, that parametric curve C. Oh, that felt good.
That was quality.
I needed that shoulder pop. I needed that. Oh. Okay. Recall that a generalized arc length is equal to this. You guys remember why? It's precisely because given some arbitrary curve, between any 2 points on the curve, we can approximate it with straight lines or secant lines. And the more and more points we pick, the closer and closer the approximation actually becomes. Right now, the approximation is not that great, but if you pick a bunch of points, it gets even better. And more points, it gets even better. And yada, yada, yada. But notice that if this is some pi minus 1, and this is some pi, and this is some xi minus 1, yi minus 1, xi, yi, and that this difference could be called delta xi, and this difference can be called the delta yi, then the distance formula between these two, which is just the application of the Pythagorean theorem, is equal to this. Is it not? Yeah, just the application of the Pythagorean theorem will tell you the distance between these two arbitrary points is equal to that. But recall that this curve C we got here is parametrized by some x of t and some y of t, equaling your f of xy. Okay, this is what creates this curve C. And so we could take derivatives. We can say df dx is actually equal to the change in y over change in x. Oh, what I meant to say is t. And what I want to call this is f prime. And actually, I want to not call this x because it gets confusing. I want to call this some f of some function of t. Set x of t to some function of t, and set y of t to some other function of t. Let's say g of t. Then f prime of t is a change in x over change in time. And so your delta x, or even your delta xi, is going to equal delta t f prime of t. And similarly, your delta yi is going to equal a delta t g prime of t. Does that make sense? The derivative is it can be approximated like this. Actually, I need to say that it approximates like this, and that g prime of t approximates to change in y over change in t. And we put an I there. So making these substitutions here, notice what we get. This is all review, right? This is from section 6. All right. So notice that when we factor out a delta t quantity squared, we get this. Right, and the square root distributes to both, so this becomes like this. And f prime of t squared is the same thing as a dx. Well, I'll introduce that when we take the limit. So when we take the limit, as these intervals become infinitesimally close to each other, where we take an infinite amount of points and the pi minus 1 and the pi infinitely get closer. Then all the deltas turn into differentials, and you get this. How does dx dt correlate to f prime of t? Well, recall f of t was x of t. So f prime of t, which is df dt, is the same thing as dx dt. And g prime of t is the same thing as dy dt. And when you square them, you get this. So this is the length of this is arc length. Review that from section 6. Why is that important? Well, because it's important in the sense that to get an area, we need length times width, and that is going to give us the length component of a parametrized curve. Okay. So that's the length, but I need the height, right? So the height is given by just a function evaluated at various t's. So the line integral of some function of x and y, ds, is going to be the same thing as the length I'll just reproduce this whole thing, times the height. And that's just a function evaluate at various t's would give you the height. Bada boom, bada bing. Oh, there's no bada boom, bada bing yet. We got to put the integral from A to B. That's where t ranges from. And now you got it. So what that ends up giving us is the ability in 3 dimensions to calculate areas of planes underneath curves in 2 dimensions or 3 dimensions. What we have highlighted here is only the 2-dimensional analog. The 3-dimensional analog will have a d dt squared, a plus d z dt squared over here, and it will have a x, y, and z of t, comma z of t over here. This is easy to generalize as that. So let's do an example. And as I said, this is a hefty section. I could talk to you for the whole class period, and we are only going to go over like half of the material in this section. But this section is very important. So on Monday, we'll be reviewing a little bit of the tail end of this section and the next section. And don't forget, next week is your exam over chapter 12. And the final will be comprehensive, but what I'll say is it will include the majority of chapter 13 stuff. The final will be mostly chapter 13 stuff. I don't want to like throw some percentages out there, but if I had to, probably 70-30. 70-30 new material, 30% old material. But as you guys know, math is just so, interconnected in nature, So, all right, here's an example. Let's calculate this line integral. Where C is the upper half of some unit circle. Okay. Here's -1, here's 1, 1, 0 actually, -1, 0. And this is our curve T. And our curve T is our curve C. Our curve C is parametric. It's parametric. This curve C has some x of t, some y of t, for its x and y coordinates respectively. What do we know parameterizes the values of a circle? Yes, sir. That's absolutely right. So we can parameterize it as cosine of t, sine t. And then just restrict t. Let's say t has to range from 0 to pi. That way at t equals 0, we're over here. And we travel across the curve all the way to here at t equals pi. So we just use what I had basically erased, that the line integral is equal to the height times the length integrated on some interval. So our f of x of t, y of t is when we stick in our parameters for x and y respectively. So this integral ends up becoming the integral from where t ranges 0 to pi of this 2 plus, and I got to replace it with the parameter cosine of t squared sine of t. That correlates to this piece. Now let's include this other piece, dt, and that's where I have to take the derivative of cosine of t and square it. Derivative of cosine is negative sine, square it, it's just sine squared t. Now I got to take the derivative of sine. Derivative of sine is cosine, square it becomes cosine squared t.
That's fine.
Doesn't it, isn't it?
That's
It is nice. You're right, Caleb. Geez, I miss having all of you guys in class all at once. The good old days. Your hair's been getting long. Mine too. No haircuts for 2 years.
nice.
Mhm.
Avid practicer of no shit November.
Yeah, I remember you had that beaver hat.
Yeah,
That was a cool hat. And now you have the tropical hat. That's cool.
It's a gift from my band section.
Oh, okay. Awesome. All right. So yeah, you are happy because this is just 1, and square root of 1 is just 1. This whole thing disappears. So now all we got to worry about is that thing over there. This integral from 0 to pi of 2 plus cosine squared t sine of t dt. Notice that this routinely decomposes because the integral is a linear operator to this. Notice that the integral of 2 is pretty simple. It's just 2t evaluated at 0 to pi. Plus, to integrate that, we can do a u substitution for cosine squared t. Let cosine squared t be u. Let cosine of t equal u. All right. And then d dt, or du dt, derivative of cosine is negative sine of t. And so du is negative sine of t dt. And so dt is negative du over sine of t. So then this becomes u squared sine of t. And then dt gets replaced with this negative du divided by sine of t. Notice that that cancels out the signs, and now we have an integral purely in u. Very good. That integral over there becomes 2 pi minus 0. And that's added to this integral, which becomes u cubed all over 3, evaluated from 0 to pi. And so what do we get here? We got a 2 pi plus, let's replace u cubed over 3 with what u used to be, and that's cosine of t quantity cubed all over 3, evaluated from 0 to pi. So this becomes 2 pi plus, let's factor out a third. This is cosine cubed of pi minus cosine cubed of 0. This is a 1. This is a negative 1. Negative 1 minus a 1 is a negative 2. So this becomes oh, but you know what, guys? I forgot that there was a negative out here. So this should have been a minus. So this should have been a minus. So that converts this to a plus. I forgot that negative that was a result of the u substitution and taking the derivative. Typical professor Niazi's thing to do. Forgetting a negative sign. Okay, so now we figured out how to do that line integral. It's easy when you can parametrize the curve easily. Sometimes you get weird curves. You gotta learn how to parametrize them. What if you have a bunch of curves? Okay. What if you have a bunch of curves? You got a curve like this, curve like that, curve like this, curve like that. Here's our C1, C2, C3, Cn. Well, what you can do is you can say that the line integral is what you think it is. You integrate about each of the curves. So let's do an example. Let's do one that's not so crazy. Let's start out like this. Where this right here is given to us by our parabola y is equal to x squared. And that's just a straight line up. And this is at 2, this is at 1, and this is at 1. And this is our x, and this is our y. So the whole thing is our curve C, but we can decompose our curve C into two curves, C1 and C2. So that the, like so, the line integral Now, how do we parameterize our curve? Well, we parameterize curves C and C1 separately. Because there is no one parameterization that works for the whole thing. You got to parameterize the C1 like so. Okay, so what we want to do, well, we want to find our function f of xy. So we want to find this. But we have a C1 and a C2 to do so. So we notice that for C1, the following parameterization holds. X is just itself, and y is, as I mentioned, x squared. And x ranges from 0 to 1. That's pretty obvious. So then,
Wait, I thought C, what, is it C or C1?
C1.
Oh,
We're talking about this first curve. So then I replace this 2x ds with what it is, but x is just x, so it's still 2x ds. And it's not actually just that, because remember that you needed your height, which is your f of xy, times the length. And here's where our ds goes. And we're integrating from 0 to 1. So dx dt doesn't exist because this is a parameterization and the parameter is x. So there is no dx dt, it's just a dx dx. And there is no dy dt, it's a dy dx. Because we parameterize it like so. It just made sense to parameterize it like this. Let x be itself, and let y be a parabola for positive values all the way up to 1. If we included a t in there, it would make things unnecessarily complicated. So dx divided by dx is just 1. When you square it, it's just 1. And then dy dx is when you take d dx of this, so that just becomes 2x. And when you square it, it becomes 4x squared. And then you just calculate that integral. You do the calculations, and what you end up getting is 5 square root of 5 minus 1 over 6 once you're done. So that's what happens when you integrate down C1. What about when you integrate C2? All right, so now we're going to have to parameterize C2. How do we do that? Well, we notice that x is fixed at 1. Notice it just goes straight up. So x is equal to 1. And what about y?
well, it's technically infinite.
Well, the slope is infinite, but what does y do?
It ranges from 1 to 2.
Yeah. So we parameterize y as itself and say range it from exactly as you said, Caleb, from 1 to 2. Don't need to introduce x or anything because we don't need to introduce t or anything like that because that would make this unnecessarily complicated. So once we do that, and we realize that this is holds 2, so we get this. And we're integrating from 0, or from 1 to 2 of our 2x, which is our 2 times 1 now, because x is always 1, and square root of something ds with these squared. And we know that there's no t. Our parameter is y. So we change this to y. Over there, you get dy over dy when you square it, and it's just simply 1. Over there, you get dx dy. And notice that dx dy is 0. So you trivially get, when you integrate this, that it equals 2. So that your final answer is 2 plus this. Okay. So there's still a lot to cover in this section, but I'm going to choose to do line integrals generalized to 3D, and then the next class period talk about the rest, and then move on to the next section. So line integrals in 3D. The generalization is not that bad. Parametrize like so. That's the parametric. Here's the vector. And what you can say is that limits as n approaches infinity. Same argument as before. Now there's just a z. We've derived that this is a three-dimensional distance formula. That decomposes to, as you'd expect, the line integral across the curve C of your x, y, z, square root So also, let's say we want t to range for some energies. So to finish class off, let's do something where we apply this to this problem. What about something like this? Where C is a circular helix. given by x is equal to cos x of t equal to cosine of t, y of t equal to sine of t, z of t is just t, and t ranges from 0 to 2 pi. That's all you got to do. You use that right there. A and b turn to 0 and 2 pi. F, our function, we replace the y with its parameterized value in t. We replace the z with its parameterized value in t, as z is t, and then we take those derivatives and square them and add them. Dx dt squared is derivative of cosine is negative sine. Negative sine squared is positive sine squared. Derivative of y with respect to t. Derivative of sine is cosine. Cosine squared. Derivative of z with respect to t is 1. 1 squared is just 1. We notice that right here, this is a 1, and it's really 1 plus 1. So this whole thing just decomposes to a root 2. And we can just have that root 2 outside the integral. Or it's a sine squared t. Oh, and that should be a. This should say dt, not ds. And you guys know how to integrate that. What you end up getting is a square root of 2 pi as the final answer once you integrate. So pretty straightforward, right? If you know how to do the line integral. Yeah, that's a 3-dimensional version of it. Now you can do line integrals inside vector fields, and they have physical consequences. It's really cool. It's like having a charged particle in an electric field or a magnetic field and seeing how it influences it. Just like how when you take the integral of a force function off of some displacement, you get the work. Very much like that. So we'll talk more about that next class period. In the meantime, keep turning in your work. The fact that you don't have grades for it is a good thing. I'm just gonna do homework and quizzes for completion. I've stopped even giving quick quizzes. I don't want to have to enter all those quizzes in. Okay, so what we'll do is homework will be completion from now on. Some of them in the earlier semester were graded, but from now on they'll just be completion. For you guys, there's lots of resources on the internet. So if you want to know how to do a problem, you can just look it up and have that as a resource to how to do the next problem. So I suggest doing that for a few problems to get the hang of it, and then try doing it on your own and significantly struggle with it and see if you can solve it all on your own. Because on the test, that's the situation you're in. So, but yeah, there's nothing wrong with using resources. The internet is a great resource if used properly. I don't mind if you guys, unless you use it properly. And about your exams, they will be handed back to you on Monday.
Not looking forward to that.
Well, the thing is, you know how all the power went out? Yeah, that threw a wrench in things. Our power didn't go out, but my whole wife's family and my side of the family, there's 12 people in a 2-bedroom, 1-bathroom house. There's no getting anything done at that point. So
That sure makes it fun.